Okay, great. Good afternoon, everybody. So, welcome to today's NC-CAV seminar um, on the intersection capacity adjustment considering different market penetration rates of connected and autonomous vehicles. I would like to thank the sponsors of the project and CDUT for enabling this research, as well as industrial partners and community partners, Downtown Greensboro, Verizon, and RTI. Before starting the talk, please allow me to talk a little bit about today's speaker, Dr. Lee Song. He received his PhD degree in transportation engineering from University of North Carolina at Charlotte, and his master degree from Harbin Institute of Technology, and bachelor degree from Shanghai Maritime University. Actually, I believe he's the first graduate student of NC-CAV that has been graduated. With that, Dr. Song, the floor is yours, and let me stop sharing and feel free to share and start your talk. Thank you so much.
Thank you, for Dr. Adhala, and also thanks for the Professor Ali to give me this opportunity to share and present my research in the NC-CAV. Oh, so you can see my screen now? Is that all good?
Yes, we do.
Okay, good. Good afternoon, everyone. It's my great honor to present my research in intersection capacity adjustment considering different market penetration of connected and autonomous vehicles. And my research is under the supervision by Professor Wei Fan from UNC Charlotte. And the main objectives of this project is to first conduct a comprehensive review of the state of art and the state of practice on CAV technologies and their impacts on intersection capacity and associated transportation revenues. A second objective is to develop case studies to illustrate this impact, considering the impact of this existence, particularly on intersections. Suitable intersections will be identified for the case study. And third one is to create simulation methods to measure intersection capacity at different CAV possible market penetration levels. And fourth is to analyze the impacts of CAV technologies on intersection capacity and provide recommendations for future research directions. The hypothetical intersection scenarios and the empirical capacity analysis is illustrated in the following two figures. The left one illustrates the empirical method for intersection capacity analysis, which mainly include the first for the traffic movement at the intersection, the signal phase plan, and the critical volumes from different in approach lengths, and also the sum of critical volumes, and finally calculate the capacity of that intersection. And the right figure illustrates the layout for the intersection configuration and the basic signal phase for the simulation intersection. Based on the capacity analysis method, we can calculate first for a pre-timed signal scheme for that intersection, and also based on that signal schemes, we can calculate intersection capacity based for the hypothetical isolated intersection, which is around 5,592 vehicles per hour. And this value is set as a basement for simulation. As shown in the table 1, we have already get a lot of adjustment factors for the simulation saturation flow rate recommended from the highway capacity manual. For example, we can get adjustment factors for the capacity based on the lane width, heavy vehicles percentage, and also for the approach grade. Based on that, we can get a specific formula to adjust for the saturation flow rate. By doing that, we can also get a specific adjustment factors for saturated traffic flow under different market penetration rate of CAVs, which is the main goal of our research. So in order to get that adjustment factors, we setting for a basement of basic simulation. That simulation first sets for the traffic simulation model for the human driving vehicles and also for the connected and automated vehicles. For human driving vehicles, this research used the intelligent driving model, which is first proposed by the Tiber in 2000. And also for the simulation of CAVs, the adaptive cruise control system and the cooperative adaptive cruise control system are utilized, which is mainly based on the previous work of the Liu in 2018 and Xiao in the 2017. In this research, when CAV is following a human driving vehicle, then the car following system is changed into the ACC mode. When the CAV is following another CAV, then the car following system is switched into a CACC mode for a closer car following gap behavior. The basic parameters for the specific traffic simulation models are illustrated as follows. The desired time gaps for human drive vehicles and CAVs are set as 1.9 seconds and 0.6 seconds for CAVs. And also we set 1.1 second for CAV with ACC system, which means that the CAV has no following vehicles, or it has no front vehicles within the sensor gap. To model heterogeneous driving behaviors of human drivers, the maximum speed for the human drive vehicles follows a normal distribution with respect to speed limit. Also, other parameters for CACC control CAVs are set according to a previous research, especially for the UC Berkeley's PATH program. The default lane change mode LC 2013 in Sumo is employed for all vehicles. And the table 2 illustrates the basic parameters, including the acceleration, deceleration, the desired time gaps, speed deviations, and the minimum following gaps for different kind of vehicles. The table 3 also illustrates the basic parameters for specific traffic simulation models, including the minimum gap, the maximum deceleration, also including some factors as the speed control gains, the collision avoidance gain space. By using the default values in the second column, we can set different traffic behaviors for CAVs, human drive vehicles. With the basement settings for simulations, we also create specific scenarios for the simulation, which is for the first one is for the lane group level analysis. As defined in highway capacity manual, the saturation headway is the average headway between the 5th and the 15 passenger vehicles in a standing queue when the intersection signal changes from red to green. The first 4 headways are not included due to the start-up loose time. The headway is calculated by the time gap when 2 successive vehicles, which means the front bumpers of the vehicles passing over the stop line, which is illustrated in the left figure. And also we can calculate the saturation headway with considering for the start up loose time, which is illustrated in the left figure. With the basement settings for the simulation scenarios, we can first calculate the saturation headways for each land group at the intersection during the simulation. The table 4 illustrates saturated headways for each land group, which we can observe different saturation headways under different market penetration rate of CAVs. We can observe that, for example, for the exclusive through traffic lane, we can observe a decrease in the saturation headways with increase of the market penetration rate of CAVs. Also, in CAVs with the ACC or CACC mode, we can calculate the gap based on the right formula, and also we can calculate gap for human drive vehicles in the IDM mode based on the right figure. Considering the impacts of CAVs and we get the saturation headways, then the next step we can calculate the saturation flow rate star S star, which is adjusted by the headway adjustment factor FH according to the equation in the right, which means that we can calculate the FH adjustment factors for the saturation flow rate under different market penetration rate of CAVs. And the table 5 summarizes the result for the adjustment factors for the saturated headways according to the highway capacity manual. Also, we can see that, for example, for the exclusive through traffic lane, then with the increase of the CAV rate, we can also observe a decrease in the values in the adjustment factors for the saturation headways. And in the right figures, we can observe a substantial decrease for the saturation headway factors for the exclusive traffic through lane, the exclusive left turn lane, and also for the shared right turn lane for under with the increase of the market penetration rate of CAVs. After that, we can also calculate the saturation flow rate factors, which is specific for the all capacity of the intersection, and by doing that, we can calculate the capacity adjustment factor FC, which means that we can calculate the capacity of that intersection under different market penetration rate of CAV. And table 6 summarizes the adjustment factors for the saturation flow rate for the whole throughput of the intersection, which means that we can see with the increase of the CAV market penetration rate, we can observe the increase in the saturation flow rate adjustment factors for the capacity of that intersection. For example, we can observe above 2.268 for the exclusive traffic through traffic lane under 100% of CAVs, which means that the capacity of that intersection increased about 126%. The tendency of the exclusive through exclusive left and shared right turn lane of that capacity adjustment factors are all observed in the figure 3. After calculate for the adjustment factors for the specific lane, we can also do an intersection level and analyze this, which means that we calculated the adjustment factor for the whole intersection. The simulation maximum throughput, which is identified as the maximum capacity of that isolated intersection, is obtained with the increase of the traffic demand under different market penetration rate of CAV condition, which means that with increase of the traffic demand, then in the simulation, we can observe a steadily increase in the throughput at first. After a certain volume, we can observe the saturated traffic at that intersection, and that maximum volume is set as the maximum throughput, which is also identified as the capacity of that intersection. The right table, the table 7, also summarizes the intersection performance, including total waiting time, the average waiting time, the total carbon dioxide emissions, the average carbon dioxide emissions, the total fuel consumptions, and average fuel consumption for the intersection with the increase of the traffic demand. We can observe that for that isolated intersection, we can with 5,400 vehicles per hour, we can observe the saturated throughput, which is around 4,638, which is pretty close to the capacity we have calculated by the formula. And by doing that, we can calculate the maximum throughput under different market penetration rate of CAVs, which means that we increase the market penetration rate under different simulation scenarios, and by increase of the traffic demand, we can finally observe a maximum throughput, which is treated as the capacity for that scenario. Within that, we summarize the traffic throughput under different market penetration rate of CAVs. It is clearly that with the increase of the market penetration rate, we can finally get a increase in the maximum throughput under different scenarios. By doing that, we get the maximum throughput under different market penetration rate, and which is shown in the figure 6 as the red dot. And with the maximum throughput under different market penetration rate of CAVs, the fitting curves of the maximum throughput with regard to the market penetration rate of CAV is obtained. And the fitting equation is also shown in the figure 6, which is showing the figures, and the traffic engineers can use that equation to get the fitting curve is used to calculate for the whole capacity of the intersections directly under different market penetration rate, only considered for the market penetration rate of the CAVs. The table 7 present the detailed values of the traffic performance under saturated traffic flow with different market penetration rate of CAVs. And we can also observe for the change rate of the throughput with, for example, for scenarios with only 10% of market penetration rate of CAVs, we can observe about only 2% increase in the throughput, and that with the increase of the market penetration rate, then the change rate also increase, which means that the throughput increased steadily. And with 100 market penetration rate of CAVs, we can finally observe about the change rate of 1.7, which means that we can observe the 70% increase in the throughput with regard to scenarios with only human drive vehicles. After doing that, we also calculate and present the fitting curves of other performance criteria with regard to different market penetration rate of CAVs, which include the cumulative carbon dioxide emissions, the cumulative fuel consumptions, and the total waiting times for the whole intersection. And also we observe for the average carbon dioxide emissions and the fuel consumption, the average waiting time on the different market penetration rate of CAV. It is observed that with the increase of market penetration rate of CAVs, a decrease in the average volume for the carbon dioxide emissions and the fuel consumptions and the waiting time are all observed. After that, we also investigate the impact of CAV's penetration rate on the intersection with fixed traffic demand, which means that in these simulation scenarios, we fixed the traffic demand, and after that, we consider the variations in the market penetration rate. The hypothesis of these scenarios is the impacts of CAV penetration rate are different under different demand levels. For example, in Figure 7, we can observe and calculate the maximum throughput with 100 market penetration rate of the human drive vehicles. And also, in scenarios with 100 market penetration rate of CAV, we can observe that the maximum throughput increased to 1.7, which means that 70% increase are observed for the maximum throughput. And we can also by getting these two different maximum throughput, we want to test the impact of CAV penetration rate with the increase of the demand levels from 0 to the capacity with only human drive vehicles and the capacity with only CAV vehicles. For the first simulation scenarios, we test the performance of the traffic in the hypothetical isolated four-way intersections, and with the increase of the traffic demand, we can observe the three different tendencies for the average waiting time. For example, for the first stage, with the demand under 0.2 capacity with only human drive vehicles and the demand with only 0.6 multiply the capacity with only human drive vehicles, a slightly increase of the average waiting time is observed in that scenario. Well, with the demand O is over 0.6 capacity of the human drive vehicles into the capacity with 100 market penetration rate of only human drive vehicles, we can observe a steadily decrease in the average waiting time, which means that with the increase of CAVs, then the average waiting time are observed decreased accordingly, which is a good result, and which means that the traffic demand for that scenario is enough to show the impact of human drive vehicles and CAVs. And for scenarios with overcapacity, which means that the demand is over the capacity with only human drive vehicle scenarios, we can observe a oversaturated traffic flow under certain market penetration rate of CAVs. And only after certain market penetration rate of CAVs, we can observe a decrease in the average waiting time accordingly, which is by doing simulation scenarios with the increase of traffic demand from 1.1 C capacity of human drive vehicles into 1.5 multiply the capacity with only human drive vehicles. Those results are also summarized in the figure in the right, which means that only after certain traffic demand, we can observe a decrease in the average waiting time when increase the market penetration rate of CAVs. Well, for scenarios which is oversaturated, which means that the traffic demand is larger than the capacity with only human drive vehicles, then at first we will observe oversaturated in the intersection, and only after certain market penetration rate, which is around 40% market penetration rate of CAV, and after that volume, after that critical volume, we can observe a decrease in the average waiting time accordingly. By summary, for that hypothetical four-way intersection, we can just like to segment the traffic performance into three different stages. For the first stage, stage 1, with the traffic demand under 0 to 0.6 multiply the capacity of human drive vehicles, then under that scenario, the total waiting time would increase slightly, which means that we cannot observe a significantly impact of CAVs under under that scenario, and only when the traffic demand for the intersection is between 0.6 capacity of human drive vehicles and under the 1 multiplied capacity of human drive vehicles, then the total waiting time would decrease accordingly. Which means that with the increase of CAV percentage, we can observe a steadily decrease in the total waiting time. And when the traffic demand is oversaturated, which means that it is larger than the capacity with only human drive vehicles, and also less than the volume of the capacity of only CAV vehicles, then the total waiting time would increase initially, which means that at first stage the traffic will be oversaturated, and only after certain market penetration rate we can observe a decrease in the total waiting time. And that to test for that scenarios, we also do the case studies with specific traffic, which is obtained from a real-world intersection. The first intersection is an isolated intersection in Charlotte, North Carolina, and we observed a pre-time signal scheme for that isolated intersection from the NC-DOT, and also get the traffic volume of each traffic movement of that intersection. And by doing that, we can setting for a simulation for that intersection, and we can increase the traffic demand. The left figure, which in the green box, which means that the traffic demand is for the real world traffic demand, and we increase that traffic demand to 25% and also 50%. With specific scenarios with under different traffic demand, we can all observe a decrease in the total waiting time for scenarios with increase in the CAV penetration rate, which is very close to the stage 1 and stage 2 for the first simulation scenarios. And also we test the traffic performance at 2 adjacent intersections in Greensboro, North Carolina, which is showing the layout is shown in the middle figures, and also the right figure, the middle, identified the pre-time signal schemes of the first intersection and also for the second intersection. With all that as the input for simulations, we can test the traffic performance under different different traffic demand. For the first one, we can observe that the traffic demand is very low, so that with the increase of CAV, we observed a slightly increase in total waiting time. For that case, we double the traffic demand and test for the total waiting time performance. At first stage, we can see an oversaturated scenarios, and only after 60% of the CAVs penetration rate, we can observe a decrease in the total waiting time, which means that total waiting time would increase initially and then decrease only after a certain market penetration rate, which is also the traffic performance is also very close to the hypothesis, the stage 2, stage 1 and stage 3. That's all my presentation today. Thank you for your listening. Any questions and suggestions are all welcome.
Thank you so much. So, any question? So, while others are getting prepared for the questions, I do have one question. And you might have already mentioned it, but it could be helpful if you can remind again. So out of all these scenarios that you were discussing, what was best scenario or best situation that you saw that you can gain most for the for increasing the capacity of the intersection. Which sort of scenario was you think that might be increasing, providing most capacity?
So that's a very good question, and I want to say is that when the traffic demand for that intersection is not larger than the capacity of with only human drive vehicles, then we can observe a steadily decrease for the total waiting, which means that the capacity will increase steadily. And for the hypothetical intersection, we can observe about 70% increase for the capacity, and which means that only with the traffic demand is lower than 1.7 multiplied the capacity of human drive vehicles, then within that range we can get the maximum capacity. And if we test the traffic demand over 1.7 capacity of human drive vehicles, then we will not observe another gain in the capacity. That is the results from simulations of the hypothetical intersection. But that critical volume 1.7 will change for different types of intersections, which means that we will always get a critical volume for different kind of intersections with different layouts. That's the result in my simulation. Did that answer your questions, Professor?
Thank you. Yes, and one more question. Again, you might have mentioned it, but I missed that part. What was the simulation platform that you have been using for all these simulations?
Well, I have used for open source simulation from a platform which named Sumo, SUMO.
Okay, and what's out of making all these simulations? What do you think as far as the simulation platform? How happy you were about this simulator, or what do you think that might be improved to make the simulation results more realistic?
Well, that's a pretty good question, because the simulation is only it has a gap from the reality. So in these simulations, we have used at the first stage we have tested different adjustment factors for the car following models, which means that we want to approximate the real world traffic flow as to just like to adjustment factors in the intelligent driving model, and also for the adaptive cruise control mode from for the CAVs, and especially for CAVs, because currently we did not equip with the of the vehicles to test adjustment factor. So we have adopted the adjustment factor from the UC Berkeley's PATH program, which has tested the traffic flow under a real world test. So that's what we have do currently to make the simulation as much as close to the real world scenarios.
I see. Okay, great, thank you. Oh, any other question? Benjamin, you should have maybe similar sort of questions. Do you have any, Benjamin? To some degree, this talk might have some overlap with your research too, a little bit at least. So in that sense, you might have questions here too.
That's yes. Because I have do this research and test different results, and I also want to know, because there still have a gap between the CAV vehicles for simulations. There has no just like certain car following models for CAVs. Different research has used different car following models in simulations, and in this program, we have used the framework from the past program, which is conducted by the UC Berkeley's researchers. But for other research papers, they have tested, for example, for some research using the Vision simulation platform, they have used the W99 adjustment factors for those. So I still very interested to know the gap between different research with different coupling model for CAVs. What is the performance difference between those two kind of vehicles? Because currently the simulation is not we cannot say which one is better. You know what I mean.
I see. Yeah.
So that's what I interested for. Maybe in the future we can test just like set as one research as a benchmark and test with other research coupling models to see the difference between those works.
I see. Okay. Right. So, any other question? If not, thank you again, Dr. Saling, and wish everybody a great weekend.
Thank you, Professor.
Thank you, and happy Thanksgiving in advance, because I don't think that we do have a meeting next week. Thank you. Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.